Hello, welcome everyone. In today's lecture, we are going to again look at a new concept, which is called stress concentration. Again, this is going to be a very brief introduction to this concept. You will learn this in a lot more detail when you go to your 342, which is your design class. Okay. So let's start with the objectives of this class. So by the end of this lecture, you will be prepared to do two things. One is you will understand the concept of stress concentration, and then you will be able to analyze the stress concentration in flat plates due to circular holes. Okay, again, this is a very simple example, but it's relevant to the lab that you'll be performing that is attached to this class. So essentially, this introduction to stress concentration is just to make sure that the lab that is attached to the class kind of makes a little bit more sense for you. Okay, so what is a stress concentration? A stress concentration is essentially a large increase in stress in a localized region. Okay, that is the important part. Okay, of a structure. Okay, and why does this increase in stress happen? Okay, it usually happens because of a variety of factors. So there could be changes in geometry. Okay, there could be changes in material properties along the structure. There could be abrupt changes in loading. For example, whenever you have a concentrated force or a moment, you can have a localized increase in stress. Okay, and there are also certain other factors that can contribute to stress concentration. These are essentially not intentional. So for example, you can have cracks in the structure, which can be internal cracks or external cracks. You can have roughness on the surface, you can have porosity, and so on and so forth. Essentially, these are material defects that can also contribute to stress concentration. Okay? Now, if you want to think of examples of stress concentrations, basically they are everywhere. So essentially, if you look at any engineering structure, you're going to have at least one of these things. There's going to be a change in geometry, there is going to be a change in material property, or some kind of crack, or changes in loading, anything of that sort. So if you think of plates that are being used as structural materials, usually these plates have holes, they have rivets, they have notches, they have welds. All these places are potentially places of stress concentration. Or if you think of a shaft, right? Many shafts basically are stepped shafts. Essentially, you'll have one diameter in one particular area and another diameter in a different area, and so on, right? So the steps where there is a change in the diameter, those are essentially points of stress concentrations, or the keyways by which you essentially mount a gear or a pulley to a shaft. That could be a point of stress concentration. So essentially, pretty much any structure that you design that is used for a practical purpose has some stress concentration. So the idea is basically to either analyze these things properly so that you can have sufficient factor of safety, or you make changes in the design so that you can reduce or mitigate the stress concentrations. Okay, so we'll look at a little bit of both in the following. Okay, so first we will look at a very specific example of a stress concentration in a hole or in a plate with a circular hole. Okay, so this is a very simple example. Essentially, you have a plate that is subjected to a uniform tensile load. Okay, the stress that is far away from this hole here is sigma naught. Okay, the sigma naught is nothing but P over A, where P is your axial force and A is the cross-sectional area of your plate. Okay, so you can assume that the plate has a width W and maybe a thickness T. Okay, now if you look at the stress in the point where the hole is present, okay, if you look at this cross-section here, there the cross-sectional area is a little bit smaller than the cross-sectional area here. Okay, so essentially, if this area is A, this area is some A prime, and A prime is smaller than A. Sorry, is less than A. Okay, and how is A prime and A related? A prime is essentially A times W minus D divided by W. Okay, so if W is the width of the plate here, and the effective cross-sectional area, A prime is going to be W minus D times W times A. Okay, so if you find out what is the stress not at the far field, but actually in the cross-section where the hole is present, that is what is called as a nominal stress. Okay, and that is going to be nothing but sigma naught times W by W minus T. Okay, essentially, it's inversely proportional to the area. Okay, so this stress is called a nominal stress because in some sense it is the average stress in that cross section. Okay, but that is not the maximum stress the structure feels. Okay, that is something that you must keep in mind. Okay, so this sigma nominal, you can think of it as the average stress in the cross section where the hole is present. Okay, but the actual stress or the actual maximum stress in that area is going to be quite different. Okay, and that essentially you can find out by using what is called as a stress concentration factor Kt. Okay, so essentially you have an average stress in the cross section where you have the hole, but the maximum stress in that cross section is going to be different, and that is given by this ratio sigma max over sigma nominal, which is given by the stress concentration factor. So if you want to kind of think of it in another way, the maximum stress is going to be Kt times sigma nominal. Okay, now if you look at a cross section like this, okay, and then you look at the stress profile in that cross section, it is going to be very, very non-uniform. Okay, so that is what we're going to look at next. Now, if you look at this cross section here, what I've done is I have taken a cross section right along the center of the hole, okay, and I isolated the left part. Okay, so now if you look at this point B, which is at the edge, and this point C, which is basically at the edge of the circle or the edge of the hole at the middle of the plate, then the stress at this point C is going to be maximum, just sigma C, and that is going to be the stress concentration factor Kt times the nominal stress. Okay. On the other hand, if you look at the stress at this point B, it is going to be less than sigma nominal. And the reason is because the average stress is sigma nominal. So if some portions of that particular cross section are going to have stresses greater than sigma nominal, which is clearly the case at point C, then there has to be some parts or some points in that cross section where the stress has to be less than sigma nominal. Okay, so sigma B is usually quite a bit smaller than sigma nominal, and sigma C is quite a bit larger than sigma nominal. Okay, now this Kt, which is called as the stress concentration factor, depends on two things. It depends on the diameter of the hole D and also on the width of the plate W. Okay, and this graph here essentially tells you how the stress concentration factor changes as a function of D over W. Okay, so now when you have D over W to be equal to 0, what it essentially means is that you have a plate that is of infinite width, or a hole that is infinitesimally small. Okay, so effectively in cases where the diameter of the hole is much, much smaller than the width of the plate, you have a stress concentration factor of 3. Okay, so what it essentially means is that the stress at this point C is going to be 3 times the nominal stress along that cross section. Okay, but as you increase this D over W ratio, so essentially the hole gets proportionally larger compared to the width, then the stress concentration factor keeps reducing. So essentially if you get to about a D over W ratio of 0.8, the stress concentration factor is going to be around 2.2. Again, this is just an empirically derived curve. So that is how the stress concentration factor looks like. Now you might think that, okay, if I have a larger hole, I have a smaller stress concentration. So am I better off having a larger hole compared to a smaller hole? Okay, that is not quite true because your stress concentration factor is going down with the higher D over W ratio. On the other hand, your sigma nominal is also increasing. So if you think about this sigma C here, it depends on 2 factors, the Kt value and also the sigma nominal. This reduces with D over W increasing. On the other hand, this increases with D over W. Okay, so what matters is the product of these 2 terms. Okay, so usually what you will find is that if you have a larger hole, then you'll have a higher maximum stress. Okay, so that is what we'll look at in a specific example in the following lectures. Okay, But the main thing that I want you to notice is that the stress concentration factor reduces as the d over w ratio increases. But on the other hand, the nominal stress also increases. Actually, the nominal stress increases. The kT reduces and the nominal stress actually increases as the d over w ratio increases. Okay, that is something that you must keep in mind. Okay. Now, effectively, if you want to find out the maximum stress in a plate that has a circular hole and that is subjected to a uniform axial force, then you have 4 steps. First, you find the far field stress, sigma naught. Then you find out the nominal stress in the cross-section where the hole is present. Then you find the kT value based on the d over w ratio, the diameter of the hole to the width ratio. And then essentially use sigma max equal to kT times sigma nominal to find out the maximum stress in the plate. Okay. Now, I want to kind of talk about a couple of things here. This particular kT versus d over w curve is only true for circular holes on flat plates. Okay. And it is only true for the case where you have a uniform tensile load. Okay. If you take the same plate with a hole, but now if you bend it, the stress concentration factor will be different. Okay. The stress concentration factor essentially depends on the geometry. It depends on the specificity of the stress concentration that is there, whether it's a hole or a crack or an elliptical hole, whatever it is, that matters. And also the type of loading. Okay. So essentially you can't use this graph universally. Okay. You have different graphs for kT for different types of stress concentrations and different types of loading. Okay. Again, you will look at these things in a lot more detail when you go to your design class. Okay. But here I just want to mention that this is not some universal curve that you can use. Okay. So the last thing that I want to talk about is how to reduce stress concentrations. Okay. So if you think of something like a shaft, okay, where you have a diameter d1 in one part of the shaft and a diameter d2 in the other part of the shaft. Okay. So this point here, where there is an abrupt change in geometry, is going to be a point of stress concentration. Okay. So one way to actually reduce this stress concentration is actually remove material in the low stress region. So essentially this region is going to be higher stress and this is going to be lower stress because the diameter here is higher, right? So essentially, if you want to have a lower stress concentration factor, you essentially remove material from the lower stress areas. Okay, so essentially what you do is you take a stepped shaft that is like this, which is abruptly changing its diameter, and then essentially make it into a smooth change in diameter. Okay, and by doing that, essentially you are removing the material here, right? You end up reducing the stress concentration. Okay, you can also have it, instead of having a linear change, you can essentially have a smooth change, essentially using a circular kind of profile or something else. That will probably even reduce the stress concentration even more. Another thing that you can do, which is actually similar, is to actually make holes in these areas. Okay, and these holes are what are called as stress relief holes. So it essentially has the same effect as removing material like this. Okay, when you go from here to here, essentially you're removing material. And essentially you're doing the same thing here. So instead of removing the material completely, you just put a few holes inside the shaft. Okay, and that reduces the stress. Okay, so there are multiple ways to reduce stress concentrations. So instead of, another way to kind of do this is essentially make sure that this another way to kind of do this is essentially make sure that these particular corners are rounded instead of being at a very sharp angle. Okay, so essentially you can reduce stress concentration by rounding off corners, removing material, make sure that the transitions are smooth, and so on and so forth. Okay, so there are many ways to reduce stress concentration, and this is something that is very important to do because, as we will see later, a lot of times, cracks that form during fatigue originate from stress concentrations. So essentially, if you reduce the stress concentrations, you reduce the chances of a fatigue crack being initiated, and that essentially means that the lifetime of your component is going to be extended. Okay? So again, this was a very, very short and brief introduction to stress concentrations, and we look at like one or two examples later on. Sure. Thank you.